Sometimes we encountered a composite function f of fx. Now, in general, this equation here is not solvable. But there's some special case where f is a quadratic polynomial. We're going to talk about that, and we're going to look at the final problem, problem 25, from the 2021 AMC10. I believe that is also appeared in the AMC12 in the same year. Okay, so let's look at one example. For example, we have quadratic here, x squared minus 2x minus 3, and we try to find x for which f of fx equal to 0. How would you address this? Now, one way, of course, you try to see, since f, the function here is quadratic, is given, you can calculate f of fx. So if you try to do that, what you're going to do is you're going to plug in the expression here into the function f. Plug in itself to itself, basically. All right. So here, the next step would be you plug in here, because this is fx, and you plug into minus fx and minus 3. And then if you try to expand this, you will know that this is going to be square, right? So you're going to have x to the 4th power. This polynomial is going to be degree 4 polynomial. And in general, you'll try to solve it, for this polynomial equal to 0, you may have up to 4 roots. It could be real number or complex number, right? Now, however, we're going to look at it from different angle, because we don't know how to solve equation degree 4, right? So you try to try and errors or try to factor the polynomial, which may not always be easy. But here, let's look at another angle here. So what is the meaning of f of fx equal to 0? So let's say for given x, fx would have a value, right? So let this value be r, let's say. If fx equal to r, then f of fx would be fr. What we're saying here, for this equal to 0, we know that fr would be 0, right? So fr would be 0. So what is the meaning of that? That means r is a root of fx equal to 0, right? So r is a root. In this case, r is a root of this particular quadratic because we're given the quadratic, right? So of course, this is easy to solve. You can know that if you factor it, right? So x would be 3 or -1. In this case, we say r, right? So r would be 2 values, right? So r1 and r2. Now, how do we find x? We know that fx equal to r. We need to find that x. Now, that x would satisfy f of fx equal to 0. Okay? So in other words, we're dealing with 2 equations here, right? So 2 equations would be this fx equal to r1 and r2. Now, these 2 quadratic equations can be solved. In this case, each has 2 roots, right? So we can solve it here. For the first equation, we get these results. For the second one, we get these. Now, we have found the 4 roots of the equation f of fx equal to 0, right? So that's better than the previous approach where we try to expand the polynomial into degree 4 polynomial, right? So let's look at a problem from AMC10. That's problem 25, usually the most difficult one. So here, we introduce a terminology saying that the quadratic here with leading coefficient of 1. A lot of times it's easier to deal with a coefficient where the leading coefficient is 1. And we said this is disrespectful if the equation here is satisfied by 3 real numbers. Okay, earlier we know that sometimes you have 4 real numbers satisfy the equation, but in this case there are exactly 3. Right? So we call all those polynomials a disrespectful polynomial. And among all those, there's a unique one, tilde px, for which the sum of the roots is maximized, right? So for that polynomial, we call it tilde. What is the tilde of 1? P of 1. In other words, when x equals 1, what is the value, right? So how you would approach to this problem? Of course, earlier we did analysis, and we're going to go with the second approach, which is for P of Px, right? So let's look at this problem here. Exactly 3 real numbers. That's good information to know. So earlier, as we analyzed, so if Px equal to 0 is a quadratic equation, right? And P of Px equal to 0 is degree 4 equation, right? So we let R be Px, yeah? So R here is the root of Px, so we have PR equal to 0. Then if you solve Px equal to R, that x will satisfy P of Px equal to 0, okay? That's what we need to do here, okay? So in this case, if s is a root, right, of this equation here, then we know that P of Ps would equal to 0, okay? Now here we're saying that there are exactly 3 such s, right? So which means there must be 2 such r's, right? So r must be 2 distinct r's, because for the quadratic equation here, you can have at most 2 roots. So which means if there are 2 r's, but there's 1 r such that there's only 1 real root s, and the other r has like 2 roots, right? This is the only way we can get exactly 3 roots here, satisfy this equation, right? Because p here is a quadratic, right? So we need at least 2r value. In other words, the original equation Px equals 0 must have 2 distinct roots. Okay, this information we know. So we claim that Px equals 0 has 2 roots and they're distinct, right? And then later we try to, if that is the case, right, we know that P would be in this form here, right? Because the leading coefficient is 1, right? So for some real number R1 and R2, R1 is not equal to R2. Right? And there are going to be 2 solutions gives the solution for P of Px equal to 0, which is Px equal to R1. In this case, just plug in the equation here. That would be the equation here. And the other case would be Px equal to R2, right? And then the quadratic equation would be here. Basically, what I was saying that this equation, 2 equations have exactly 3 roots. One of them must have like just 1 root. The other have 2 roots, right? Which one? Let's assume the first equation has exactly 1 root. In other words, discriminant is going to be 0, right? So for quadratic equation here, what are the discriminants here? Yeah, discriminant here. So we assume delta 1 equal to 0, delta 2 is greater than 0. Then we have exactly 3 real numbers. Okay, let's do that. So let's look at delta 1 and delta 2, right? So here you can expand it out. This is going to be R1 squared plus 2 R1 R2, right? You can expand this out. Okay, and then here you plus 2 minus 4, you can combine them, right? It becomes minus, right? And this happens to be the complete square, R1 minus R2 squared here. So we're going to have these. Okay, from here you know that R1 must be a negative number because this is a non-zero here, and the square would be, you know, positive number. So R1 has to be a negative number. And here the whole thing is greater than 0. How about R2? R2 has to be greater than R1. So this is how much we know. R1 is negative. R2 is greater. All right. So if R1 is negative, we can assume R1 be negative U squared, where U is positive. Why we have to do that? Because this is square. This is, you know, we try to make the algebra easier. All right. So does this make sense, right? Because R1 we know is negative number. So in that case, if that is the case, you plug into the equation number 1, what do you get? You get delta 1 equal this one. But here we said R1 is negative u squared. We plug that in. Okay, so in other words, we have this. Now R1, R2, since R1 is smaller, so R2 minus R1 is a positive number. So from here, we know that R2 minus R1 is going to be 2u, right? Take the square root of both sides. Okay, so this is how much we know. Let's recap, and let's go back to the original problem saying that we try to find the what is called a p tilde, where the sum of the roots is maximized. What is the sum of the root? In other words, R1 plus R2. What is that? So let's figure it out. Here, R1, we know that R1 equal negative u squared. From R2 here, you can express R2 in terms of u, right? This is R2. Now we know that R1 plus R2 is going to be this. This is actually a quadratic in u. What is u? U is some positive real numbers, right? So here you can complete the square. So you're going to get this. And here you complete the square is u minus 1/2 of square. And then you have to minus 1/4 to get rid of the constant term. So in other words, if you complete the square, this becomes this one. So we know from this, the maximum value is achieved when u equal 1/2. Okay? So let's go back to the original problem. We said that there are exactly 3 real numbers. From earlier analysis, we know that px will be in this form here. And we know that R1 plus R2 is going to be here. Maximum value is achieved when u equal 1/2. And tilde, p tilde x here, we can, find the expression for that. So let's go. So when u equal 1/2, this sum of the roots is maximized. We are looking for p tilde. The sum of roots is maximized. So here u equal 1/2. You plug in and get R1 equal negative 1/2 squared. That would be negative 1/4. And R2 would be 3/4. Right? So let's plug that into this R2 here. Negative. Yeah. And here you can find the value here. Okay. So here px, this expression here, you just plug in. So p tilde, the special, this unique polynomial here is going to be this. And for p1, you just plug in. Okay. So the final answer will be A. Okay. All right. So hope you like the video. Yeah, please share and subscribe to the channel.